The first law of thermodynamics states that the change in internal energy of a system is equal to the heat added to the system minus the work done by the system. The second law of thermodynamics tells us that the total entropy of an isolated system can never decrease over time and remains constant only if all processes are reversible. Natural processes, well, they tend to increase the total entropy of the universe. The third law of thermodynamics explains that as the temperature of a system approaches absolute zero, the entropy of a perfect crystal approaches a constant minimum.
Conduction is the process where the rate of heat transfer through a material is proportional to the negative gradient of temperature and the material's thermal conductivity. Convection. The heat transfer rate between a solid surface and a fluid, or within a fluid, is proportional to the convective heat transfer coefficient, the surface area, and the temperature difference between the surface and the fluid. Radiation. The rate of heat transfer through radiation is proportional to the emissivity of the surface, the Stefan Boltzmann constant, the surface area, and the fourth power of the difference in temperature between the surface and its environment.
Mass transfer. The mass flux is proportional to the negative gradient of concentration and the diffusion coefficient. Energy transfer. The rate of change of energy in a control volume is equal to the rate of heat transfer into the volume minus the rate of work done by the volume, plus the sum of the rates of mass flow multiplied by the specific enthalpy, kinetic energy per unit mass, and potential energy per unit mass.
General material balance. For a system in steady state, the sum of mass entering the system minus the sum of mass leaving the system is zero. For an unsteady state system, the rate of change of mass in the system is equal to the sum of mass entering the system minus the sum of mass leaving the system. Component material balance. For any component in a mixture, the rate of change of the number of moles of that component in the system is equal to the sum of the molar flow rates of the component entering the system minus the sum of the molar flow rates of the component leaving the system, plus any generation or consumption of the component within the system.